Phoenix A is often mentioned as a candidate for the largest black hole humanity has ever known, with a mass that may reach approximately 100 billion times the mass of the Sun. But that number does not come from a direct measurement. The mass that made Phoenix A famous is inferred from the energy and structures surrounding the core of the Phoenix galaxy cluster. The difficulty lies in the gap between the energetic signatures within the galaxy cluster and the actual mass of the black hole at its center. If that estimate is correct, Phoenix A is approaching the growth limit of a black hole. If it is not, the title of the largest black hole in the universe still does not belong to a name supported by sufficiently strong evidence. With Phoenix A, the title of the largest black hole does not begin with a direct image of the black hole itself, but with the traces it has left behind in the core of the Phoenix galaxy cluster. Phoenix A often appears at the top of popular lists of the largest known black holes, with a mass that may reach approximately 100 billion times the mass of the Sun, but that number must be understood alongside the method used to derive it. It depends on how scientists interpret the hot gas, the X-ray cavities, and the energy that was once released from the core of the Phoenix galaxy cluster. For closer black holes, astronomers can track the motion of stars or gas around the central region to constrain their mass. For much more distant systems, especially black holes located at the centers of galaxy clusters, the data often pass through several additional layers of modeling. Astronomers do not observe the black hole itself the way we observe a star. They read the environment around it, gas being heated, matter being pushed outward, or orbits forced to move around an invisible gravitational source. With Phoenix A, the challenge is not calling it enormous. The challenge is determining how robust the inference behind the 100 billion solar mass estimate actually is. A black hole does not shine on its own like a star. By definition, it is a region from which light cannot escape. The data come from matter and radiation outside that region. Sometimes those data come from stellar orbits around a galactic center. Sometimes they come from gas velocities. Sometimes they come from background light being bent by gravity. In galaxy clusters, the evidence may appear as cavities carved into hot X-ray emitting gas. Not every type of evidence provides the same level of certainty. A mass measurement based on stellar motion near a galactic center is not equivalent to a mass inferred from the energy required to push hot gas out of a galaxy cluster core. Phoenix A lies on the more difficult side of that boundary, distant, enormous, and interpreted through the environment of a galaxy cluster rather than through clearly measured stellar orbits. The Phoenix galaxy cluster is rich in hot gas and shines intensely in X-rays. At its center is a galaxy with an unusually high rate of star formation compared with many other central cluster galaxies. In X-ray maps, the hot gas surrounding the core does not appear as a uniform cloud. It contains hollowed-out regions, resembling the remnants of enormous energy bubbles once inflated from the cluster center. That energy source is almost certainly connected to the central black hole. But an energetic outburst is not a direct scale for measuring mass. The potential misunderstanding begins when the estimate of 100 billion solar masses becomes separated from the method behind it. When that number appears alongside the name Phoenix A, it is easy to feel as though the search is already over. In reality, that mass estimate still depends on multiple assumptions. It does not come from stellar orbits around the black hole. It depends on models of cluster core activity, outburst energy, the structure of the hot gas, and the timescale over which the black hole influenced its surroundings. If even one assumption changes, the final number can shift as well. For that reason, the title of the largest black hole cannot be secured through a single inference. One candidate may appear larger within a model, while another may appear smaller but be constrained by stronger observational evidence. At distances of billions of light years, we do not work directly with the object itself. We work with ancient light, hot gas, and models attempting to connect those signatures to the gravitational source at the center. Phoenix A remains one of the most notable candidates, but it is not yet a record that has been definitively secured. Rankings need a name at the top. Scientific data are not always that simple. At that point, the more interesting question becomes the growth limit of black holes. How large can a black hole become before the physics surrounding it begins to limit further growth? If such a limit exists, Phoenix A may be standing very close to it, or the estimate itself may be standing near the edge of what current data can reliably support. A larger black hole does not necessarily mean it can continue growing more easily. The common picture is often simpler than reality. In that picture, anything that gets close enough to a black hole is eventually swallowed. But in a real galaxy, matter does not fall straight toward the center along a simple path. Gas around a black hole rarely plunges directly inward. The gas carries angular momentum, collides with other material, heats up, and forms an accretion disk. Within that disk, matter must gradually lose energy before it can move deeper toward the central region. Some material falls into the black hole, but the rest may remain in the disk, be pushed away by radiation, or become part of outflows launched from the region near the center. On galactic scales, this process becomes even slower. A cloud of gas within a galaxy does not automatically become fuel for the central black hole. It must travel from distances of thousands of light years down to an extremely small region surrounding the event horizon. Along the way, the flow of gas is influenced by stars, dark matter, galactic structure, and turbulent motions within the interstellar medium. For that reason, gas accretion is not the only path toward creating the largest black holes. They can also gain mass through galaxy mergers. When two galaxies merge, the black holes at their centers can gradually sink toward a common core. After a very long period of time, they may form a pair of supermassive black holes and eventually merge. But even this path is not rapid. The two black holes must lose orbital energy before they can truly reach the final stage. At extremely high masses, strong gravity alone is not enough. A black hole also requires a steady fuel supply. A black hole that wants to continue growing needs a continuous flow of matter into the central region. But the gas disk surrounding it can become unstable. In the outer regions of the disk, gas can cool, collapse, and form stars before it ever reaches the black hole. The fuel still exists, but it is no longer moving in the right direction. A black hole can also disrupt its own fuel supply. During periods of intense accretion, matter near the center releases enormous amounts of radiation. Jets and winds can push gas out of the galactic core, heat the surrounding environment, and prevent gas from cooling. In many galaxy clusters, this activity leaves behind cavities in the hot gas that can be observed in X-rays. With Phoenix A, this feedback mechanism brings the story back to the problem of mass measurement. An active galaxy cluster core may be evidence for an extremely massive central black hole, but the mass of the black hole cannot be inferred simply from the impression that the system is enormous. Scientists must understand how energy was released, how the hot gas responded, and which models connect those signatures to the actual mass at the center. For that reason, the estimate of 100 billion solar masses must be traced back to the method that produced it. That estimate may come from stellar orbits, quasar light, gravitational lensing, or energetic signatures within the hot gas of a galaxy cluster. If Phoenix A truly reaches that mass range, it would represent an extreme case. But if better data eventually reduce that estimate, Phoenix A would still remain valuable as a test of how we measure the most extreme black holes. In that case, the most interesting question would lie in the limits of the measurement method itself, not merely in the size of the object. Before Phoenix A was discussed as a potentially larger candidate, TON 618 had already become the name most people associated with the largest black holes imaginable. In many size comparison videos, TON 618 appears as the upper limit of what viewers can picture. TON 618 is estimated to have a mass of tens of billions of times the mass of the Sun and sits at the center of a quasar so distant that its light began traveling more than 10 billion years ago before reaching Earth. TON 618 is not famous because it is nearby. It is not famous because we have a direct image of it. It is famous because the quasar surrounding it shines with extraordinary brightness. As matter spirals around the central black hole, becomes compressed, and heats up before falling inward, the accretion region can outshine the host galaxy itself. From that light, astronomers infer the velocity of the gas, the size of the emitting region, and the mass of the gravitational source at the center. That approach is physically grounded, but it is still an indirect measurement. TON 618 is not measured by tracking individual stars orbiting around it, as astronomers can do with some closer black holes. Its mass is inferred from the light spectrum, models of the emitting gas region, and the physical relationships connecting the observed light to the dark gravitational source at the center. For that reason, the enormous mass of TON 618 is not a number read directly from the sky. With TON 618, time itself is part of the measurement. The light being observed today does not show the system in its current state. It shows a quasar as it existed in the distant past. Since that light left its source, the system may have changed. Its gas supply may have weakened, the black hole may have continued growing, or the host galaxy may have undergone additional mergers before entering a quieter phase. For that reason, the statement that TON 618 is one of the largest known black holes always comes with an observational limitation. It is one of the largest candidates that distant light from the past allows us to measure. That does not mean we know exactly what state it is in today. TON 618, therefore, remains an important benchmark when placing Phoenix A within the search. The title of the largest black hole cannot depend on a single number alone. It also depends on the method used to infer the mass, the object's distance, the models involved, and the uncertainty attached to the estimate. The farther away an object is, the more layers of interpretation the data must pass through before becoming a published mass estimate. TON 618 does not need to be diminished for Phoenix A to become interesting. On the contrary, it serves as the benchmark that every new claim must surpass. If Phoenix A truly contains a black hole approaching 100 billion solar masses, it would not simply surpass a famous name. It would touch on a much larger question. That question concerns nature's ability to create black holes, larger than what many models have traditionally considered extremely difficult to achieve. But if the estimate for Phoenix A is not yet robust enough, TON 618 remains a reminder that a cosmic title cannot be awarded simply because a larger number appears on paper. What must be clearly separated is the origin of the estimate, the directness of the measurement, which parts come from observation and which parts come from modeling. The search is therefore not simply about replacing TON 618 with Phoenix A. The remaining question is which black hole appears larger on paper, and which black hole has evidence strong enough to hold that position. Phoenix A is not remarkable simply because of a large number. It sits inside a galaxy cluster with a hot X-ray emitting core and unusually active conditions. There, the hot gas does not remain completely stable in a diffuse state. Some of the gas appears to cool and flow toward the center, where the rate of star formation is unusually high compared with many other central galaxies in galaxy clusters. In massive galaxy clusters, the central black hole often plays a role in regulating the gas around the core. As hot gas begins to cool and move inward, the black hole can capture some of that material, become more active, and then release energy back into the surrounding environment. That energy can prevent the gas from cooling too quickly, slow the rate of star formation, and alter the structure of the cluster core. In Phoenix A, the picture does not close so neatly. The gas is still cooling. Stars are still forming at a high rate. Yet the environment around the core also carries signs of powerful outbursts. In X-ray observations, cavities appear within the hot gas as hollow regions that may have been carved out by energy released from the central black hole. A source capable of producing structures like these is unlikely to be a minor energy source. This is where the famous estimate begins to emerge. If the energy required to create those cavities is extraordinarily large, and if that energy originated from the central black hole, then the black hole itself could belong among the most massive ever inferred. Some estimates place its mass near 100 billion times the mass of the Sun. In many popular rankings, that estimate places Phoenix A above TON 618. But an X-ray cavity is not a scale. It is the trace of a process that has already occurred. To convert that trace into a black hole mass, astronomers must estimate the outburst energy, the pressure of the surrounding gas, the time required for the cavity to form, and the way energy was transferred into the cluster environment. Each step is scientifically grounded. Each step also carries uncertainty. That is the boundary between a very large candidate and a confirmed record holder. Based on the available evidence, Phoenix A remains a serious case. But the title of the largest black hole requires more than an impressive estimate. It requires a type of evidence that remains robust when models are re-examined, when new data arrive, and when the original assumptions are tested more rigorously. What makes Phoenix A compelling is that the data are too significant to ignore, yet not direct enough to lock in the title. If the estimate of 100 billion solar masses holds up, it will push the limits that black hole growth models must explain. If the estimate is revised downward, Phoenix A will not lose its scientific importance. In that case, it would demonstrate how an extreme system can be reduced too quickly to a headline and a ranking. Phoenix A therefore does not end the search. The remaining question is not which name sits at the top of a list. The remaining question is which evidence is strong enough to keep that name there. The figure of 100 billion solar masses did not emerge from a direct measurement. It was not obtained by tracking stars orbiting the central region and calculating the gravitational force acting on them. Nor did it come from a direct image of an event horizon. For a system as distant as the Phoenix cluster, those methods remain beyond our current capabilities. Instead, the estimate emerged through a different approach. Researchers examined the central galaxy, the hot gas surrounding it, and the energy required to create cavities within the X-ray emitting environment. From those observations, they used models to infer how massive the central black hole could be. Phoenix A has not been weighed directly through the motion of matter orbiting the black hole itself. Its estimated mass is inferred from the impact the central black hole may have had on its surrounding environment. This approach is not without foundation. In the cores of galaxy clusters, a central black hole can influence regions vastly larger than the area immediately surrounding its event horizon. It can push hot gas outward, inflate bubbles within plasma, slow the cooling of gas, and affect the rate of star formation in the central galaxy. If the cavities and distortions in the hot gas are enormous, then the energy source behind them must also be enormous. But the path from outburst energy to black hole mass is not a straight line. A smaller black hole operating efficiently over a long period can leave a powerful imprint. A larger black hole with intermittent activity can produce a different structure. The cluster gas itself also has its own pressure, density, turbulent motion, and evolutionary history. When those factors enter the models, the final result can change. When a scientific estimate enters popular discussion, the layers of conditions behind it are often compressed. In the research literature, a large estimate usually comes with uncertainty ranges and underlying assumptions. In rankings and summaries, those details are reduced. What remains is a simple and memorable statement: Phoenix A, nearly 100 billion times the mass of the Sun. That simplification makes the number easier to remember. It also makes the estimate sound more certain than the data actually allow. For extremely massive black holes, the distinction between possibility and confirmation is important. An estimate may place Phoenix A near 100 billion solar masses. That alone makes it a remarkable candidate. But to hold the title of the largest known black hole, that estimate must withstand independent lines of evidence or remain robust when the underlying models are tested again. Phoenix A is not a baseless claim. Observations of the Phoenix cluster genuinely reveal an energetic environment, a complex core, and a central black hole that may be extraordinarily massive. But the estimate of 100 billion solar masses should not yet be treated as a closed case. It is better understood as a milestone in an ongoing investigation. It is large enough that it cannot be ignored, yet not certain enough to stand entirely on its own. When a black hole cannot be constrained through the motion of nearby stars or gas, evidence can come from the light of an object located much farther behind it. That is the principle of gravitational lensing. A sufficiently large mass can curve the space around it, causing light from a more distant galaxy to change direction on its way to Earth. If the distortion is strong enough, the background galaxy can appear stretched, bent, or even transformed into arcs of light. In that case, the light carries information not only about the background galaxy, but also about the mass lying along its path. The strength of gravitational lensing is that it does not require a black hole to be actively accreting material. A black hole can be quiet, producing no quasar and no intense radiation. Yet if its mass is large enough and its position is favorable, it can still distort the light behind it. The case of Abell 1201 demonstrates the value of this line of evidence. In a galaxy system acting as a gravitational lens, light from a background galaxy is distorted by the mass located in front of it. By modeling that distortion, researchers can separate the contributions of stars, dark matter, and a concentrated mass at the center. If the model requires a very large central mass to reproduce the observed image, that becomes evidence for an exceptionally massive black hole. This approach differs from Phoenix A. It does not rely primarily on the energy released into hot gas. Instead, it relies on the shape of bent light. That does not make gravitational lensing a perfect measurement because it still depends on models of mass distribution. But it provides a more independent line of evidence than inferring mass from energetic feedback in hot gas. The difference lies in how closely the evidence is tied to the mass being measured. A black hole with a smaller estimated mass, but one that is tightly constrained through gravitational lensing, may be more secure than a larger black hole, whose mass depends on numerous assumptions about hot gas. For that reason, when ranking the largest black holes, the mass column alone is not enough. The method used to obtain that mass also matters. Quasars provide spectra from hot gas. Stellar motions provide orbital measurements around galactic centers. X-ray emitting gas leaves cavities and traces of energetic outbursts. Gravitational lensing leaves distortions in the light of background galaxies. No single line of evidence should stand alone if the goal is to confirm the largest black hole. Phoenix A may remain one of the most remarkable candidates in current models, but an energetic imprint in hot gas alone is not enough to transform a candidate into a definitive record holder. It requires more independent tests, or a model robust enough to turn an indirect inference into a conclusion that is difficult to challenge. Until then, Phoenix A remains positioned between an extreme estimate and a confirmed record. It may be the largest black hole ever inferred, but it is not necessarily the largest black hole constrained by the strongest available evidence. When a black hole is estimated to have a mass approaching 100 billion times that of the Sun, the issue no longer belongs only to a ranking table. It begins to touch the limits of black hole growth itself. At that point, the question becomes, how large can a black hole grow in a universe with a finite age, a finite supply of gas, and physical processes that constantly resist excessively rapid accretion? In theory, there is no simple boundary that forces a black hole to stop at a specific mass. Its event horizon can continue expanding as it acquires more matter or merges with other black holes. But in the real universe, growth depends on fuel, time, and environment. Strong gravity alone is not enough if matter cannot reach the central region. At extreme masses, the challenge is delivering enough material to the place where it is needed. To grow significantly larger, a black hole requires an enormous amount of matter to fall into the region very close to its center. Yet the surrounding gas disk can become unstable. The gas may cool, fragment into denser regions, and form stars before it ever becomes accreting material. The fuel is still present, but it is no longer flowing toward the black hole. Radiation creates another limitation. As matter falls inward and heats up, it emits intense radiation. That radiation pushes back against the incoming gas. If accretion becomes too powerful, radiation pressure and outflowing winds can drive matter away and slow the very process responsible for growth. In the centers of massive galaxies, this feedback can extend across much larger scales. Jets launched by the black hole heat the gas around the core, inflate bubbles within the cluster environment, and prevent the gas from cooling efficiently. When gas cannot cool, it becomes more difficult for new inflows to form and move toward the center. A black hole is therefore not simply a consumer of matter, it can also suppress the very supply of material that would otherwise continue feeding it. For the most extreme black holes, mass is only the visible part of the problem. Behind it lies the question of how long, and how effectively the black hole has been fed. To reach tens of billions of solar masses, a black hole must either accrete efficiently for an extended period or experience major mergers along the way. If a black hole attains such a mass very early in cosmic history, the challenge becomes even greater. It must begin with a sufficiently massive seed and exist within an environment favorable to sustained growth. Phoenix A pushes that problem to an extreme. If the estimate of nearly 100 billion solar masses is correct, it would occupy a region that many growth models regard as exceptionally difficult to reach. Not because such a black hole is forbidden by physics, but because it demands an enormous supply of matter, enough time, and favorable conditions over a very long span. That is why the estimate for Phoenix A requires especially strong evidence. The closer a number comes to a physical limit, the more firmly it must be supported by data. Otherwise, the number may reveal more about the difficulty of the measurement than about the true mass of the black hole itself. For Phoenix A, the issue does not end with whether it deserves the title of the largest known black hole. The deeper question concerns the limit of what the universe can realistically feed before the growth process itself begins to work against further growth. One issue is often overlooked in rankings of the largest black holes. The numbers are placed side by side as if all of these objects are being observed at the same moment. But the universe does not work that way. The farther we look, the older the data become. TON 618 is known through the light of an extremely distant quasar, carrying information from a much earlier period in cosmic history. Phoenix A is not observed as it exists at this exact moment either. What telescopes record is the state of the system when its light began the journey toward Earth. Everything that happened afterward belongs to a span of time that we cannot directly examine. During that time, a black hole can change. It may continue accreting matter, undergo mergers, or enter a quieter phase if its surrounding gas supply weakens or is driven away by energetic feedback. A quasar that was bright in the past is not necessarily bright today. A black hole that was growing rapidly is not necessarily being fed in the same way now. For that reason, the title of the largest known black hole always comes with a limitation imposed by observational time. It does not mean that we have inspected the entire universe at a single moment. It means only that, among the light that has reached Earth, that object belongs to the group of candidates inferred to have the greatest mass. For Phoenix A, the issue extends beyond mass alone. It also involves the epoch, represented by the light we receive from the system. The estimate of 100 billion solar masses, if correct, describes the system as it existed when that light was emitted. It does not tell us with certainty what state Phoenix A occupies in the present-day universe. That is a natural limitation of observing deep space. Every distant object is a slice of time rather than a simultaneous snapshot of the universe. Once time is added to the equation, the title of the largest black hole becomes more than a simple name on a list. It depends simultaneously on mass, measurement method, distance, cosmic epoch, and the strength of the evidence supporting the estimate. Phoenix A may indeed host one of the largest black holes ever inferred by humanity. The signatures within its galaxy cluster are strong enough that the estimate of 100 billion solar masses cannot be dismissed. But a large estimate is not the same as a final conclusion. TON 618, Phoenix A, Able 1201, and other candidates all highlight the same problem. The largest black hole in the universe cannot be identified solely by the mass listed in a ranking table. It also depends on how that mass was measured. how direct the underlying evidence is, how many assumptions are built into the model, and which moment in cosmic history the observed light represents. For that reason, the most cautious conclusion is neither to declare Phoenix A definitively the largest, nor to dismiss the possibility. What is more certain is that this title does not yet belong to a single object in any simple sense. Phoenix A remains an exceptionally compelling candidate, but to occupy the top position, it requires more than an impressive estimate. It requires evidence strong enough to support that estimate under continued scrutiny. That is where the most interesting part of the story lies. The remaining question is not simply whether the universe contains a largest black hole. It is how carefully we must interpret what the data truly allow us to claim, even when studying the largest and darkest objects we have ever encountered. Thank you for staying with Astrexo until the end of this journey. If this video changed the way you think about the title of the largest black hole in the universe, be sure to like the video, leave a comment, and subscribe to Astrexo to continue exploring deeper stories from the cosmos.